Okay. In the previous class, we discussed normalized NLMS algorithm, NLMS. Okay. I will not go through that procedure again, but this is the update equation, basic update equation we obtained. En x n vector into En divided by a scalar, which is a norm square of this. This is what we had obtained. Now, some modifications of this. Firstly, so some modifications. This norm square, if it is suppose very small, okay, that is x n has very small valued data, and therefore, this norm square is very small. That time we may result in something like a division by 0 situation, because after all it will be in computer there will be finite precision system. So, it might just be truncated to 0 and then we might have a division by 0 like situation. So, that is why instead of this we replace this by this plus one small constant, small positive constant. Since it is small, it is not going to change the algorithm much, hardly has any effect, but it will ensure one thing, the denominator will never be 0. So, the division by 0 thing will not work. Okay, that is one modification. Another is, we have done everything without assuming, assuming there is no noise. But suppose the system is like this, again I am taking just two coefficients, okay, for our explanation. So, this is your x n and some noise comes which is z n and this is d n. Okay. Let this be y n, but y n is not observable to us. What is observable is d n, whatever is coming out of the system which is mixed with noise. So, actual equation will be, since we do not know these coefficients, let us assume general weight variables w 0 x n plus w 1 x n minus 1. Okay. That should be y n, then it will be a straight line and all the previous treatment will work, but y n is not observable to us. Okay. So, if we still carry out the previous method, that is we consider this straight line, and in a more general sense we have got not just two coefficients, maybe n number of coefficients, it will be a hyperplane, not just a straight line, hyperplane. Like if we have 3 coefficients, it will be just a plane in a 3-dimensional world, and like that. Higher the dimension, we cannot call it 3-dimensional plane and all that, it is called hyperplane. In the case of 2 dimension, that plane turns out to be a straight line, as we have seen earlier. So, if I still continue with the previous method, that is equal to d n, okay, then there is a problem. This is not the actual equation is this. So, that is, but this y n is d n minus z n. Z n also is not known to us. That means, what we are doing so long, this was we took this to be our equation. The d n what is observable, and this was my w n w n. So, I was just projecting it on this, but this is not the correct straight line. Okay. So, we actually found out this much, this is what is this, that is w n vector plus this will give you this vector, which we call w n plus 1. But remember, this is not the correct straight line equation, correct straight line is this one. What is the difference between the two? see gradient remains same, W0 xn, W1 xn minus 1. So, gradient will be given in terms of xn and xn minus 1, here also xn and xn minus 1. So, they are parallel lines, but one line, I mean they cut this y axis, the intercept on the y axis is different, all right. So, they will be parallel. So, another line will be this parallel line, this is the correct line, that is W0 equal to yn, which is dn minus zn. Therefore, I should extend this to this if it is cutting on the higher side, okay. Which means in general we will not take this, we will have a constant mu brought here, which will multiply this, try to make for this much. Okay. Now, you can ask a question that how do you know that this parallel line will be above this? So, I have to expand this much, is not it? So, mu is positive, it could have gone, the parallel line could have been below, because it just depends on Zn, Zn is noise, sometimes positive, sometimes negative. So, in that case, we have to project on this side, okay, opposite of this. So, that actually should be negative that way. So, therefore, the mu that comes actually is just a mu which statistically minimizes the error between the actual update and this update, okay, this much and this much, this was the error. So, it is just for one case. So, statistically we will try to minimize this, that is why there is it is not that it will exactly hit always this, because you have chosen mu can be something else, but on an average it will be close to the correct update, this much is the correct update, okay, on an average. So, with this equation then becomes this is the NLMS update equation. Now, since we have brought in mu, because there is noise and mu cannot be, we cannot give a, I mean, if we have to be correct at every case, we have to give the corresponding mu, like here the ratio between this whole thing and whole thing, that should be mu. So, that when I multiply this by mu, I get so much, but that is for one case, but here I am choosing a constant mu. So, since I am choosing a constant mu, obviously there will be some error, okay, there will be some error, I will not get the exact update, I will get in the same direction, but a fractional update, and that is why it will no longer converge absolutely. When there is no noise, in the previous example you have shown those diagrams, you go on projecting Wn, get Wn plus 1, then Wn plus 2 and all that, eventually you will be hitting the optimal weight exactly. But the moment there is noise present in the system and you bring in a mu, okay, but mu cannot be ideally mu cannot be a constant mu, depending on case to case mu should vary, but we are not doing that. Therefore, it will not converge absolutely, but it will again converge in mean, average, expectation, that is expected value of Wn will go to W opt, not Wn will go to W opt as n tends to infinity. Okay. Those proofs I am not showing. That is, here again, sorry, we will go to W opt. Okay, this can be proved, but we can intuitively argue this way. What is norm x n square? X n is a vector, x of n minus 1 dot dot dot. I do not remember which order I took. If I say n plus 1, So, it is capital N cross 1 vector. So, norm x n square is x square n plus x n minus 1, squaring each term and adding. Okay. And now, if I suppose divide it by 1 by n, right hand side you see what is that? It is a estimated variance of x n, because I am squaring up every sample, adding over a large number of sample and averaging. So, it is approximately sigma x square variance. And x n is WSS, White Sands stationary. Now, what is trace R? R, there is trace of R matrix. R matrix is what? It is a Toeplitz matrix. Whatever element you have one diagonal, that will continue, and that is the variance here, R x x 0, correlation with gap 0, which is a variance, and same will continue. Similarly, other terms dot 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 dot, right. Trace of this will be summation of the diagonal elements. So, it will be, there are capital N of them. So, it will again be n sigma x square, right. From here I find norm x n square is capital N sigma x square, which is same as trace R. Therefore, if we ignore this epsilon for the time being because it is so small, okay, then for the time being because it is very small, we will have W n plus 1 as W n plus mu by norm x n square, which is trace R. This much into x n E n. If I call this bracketed quantity as mu prime, then it is simply LMS algorithm. Isn't it? Just W n plus mu prime, this is a constant, mu constant, trace R constant. So, this is a constant, some mu prime times and all positive, so positive constant times x n E n. Therefore, its convergence will require mu prime greater than 0, as you have seen, less than 2 by trace R. But mu prime is mu by trace R. So, if you replace mu by trace R and trace R cancels. So, you get this condition, there is a mu which you use here. Okay. So, this shows that if mu is chosen between 0 to 2, then this algorithm will converge in mean, because it turns out to be a LMS algorithm, okay, especially when order, I mean the length of this vector is large, there is capital N is large, this is a very good average. So, it is a good estimate of the variance. Okay. So, this relation holds good, norm square of x n is same as trace R, and this turns out to be LMS, okay. And from LMS convergence we can say this. But here the advantage is upper limit of mu is not dependent on input statistics, it is a constant number 2, and that is what we wanted from the beginning, because if the input statistic changes, in the case of LMS there is a problem, because upper limit is 2 by trace R, R is the input autocorrelation matrix. Okay. So, that matrix will change, but here even if input autocorrelation matrix changes, I am safe, because upper bound of mu, if as long as I keep mu less than 2, I do not care, I will always have convergence. Okay. This is the beauty of NLMS algorithm. Another thing, actually whatever I am going to say now, it comes from a more general theory called abstract vector space, but then you do not know, and neither I have any time or scope to take you to that in a course that I teach here. I cover this, and there is a vector space theory or linear algebra. Nevertheless, you have seen one thing, that suppose I give you a vector in a 3-dimensional world, okay, x as x1 I, x2 j, x3 k. Okay, equivalently, x is a coordinate, that is, it points to a coordinate. So, it can be, you can say it is a coordinate vector also like this, x1 times I, that is x direction x1 times, y direction x2 times, z direction x3 times. So, you can equivalently write like this. Similarly, suppose y is y1 I plus y2 j plus y3 k, that is equivalently y is, then dot product between them will be x1 y1 plus I dot j 0, I dot k 0, like that. So, it will be x1 y1, x2 y2 plus x3 y3, which is same as x1 y1, x2 y2, x3 y3, that is equivalent to this x transpose y, it becomes row vector. So, x1 y1, x2 y2, x3 y3, or even equivalent to y transpose x. All right. So, if I have taken a vector of length 3, it could have been any general length, say capital N. So, if you have two vectors of length capital N, their dot product will be x1 y1, x2 y2, x3 y3 dot 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 up to x n y n. If equal to 0, we say x, y are orthogonal, that is, angle between them is 90 degree in a geometrical sense. Okay. In a 3-dimensional world, you can plot the vectors. So, they will be having an angle between them 90 degree. In a general case, of course, there is no notion of angle in an n-dimensional space. So, we just say they are orthogonal if the dot product is 0. All right. Now, suppose I consider that hyperplane, any hyperplane. Okay. Say you can call it W0, this is W1, and this equation is W1 xn, xn is a data, W1 xn minus 1 is dn. This you can equivalently write as W transpose xn is equal to dn, where W is just this W0 W1 and xn we have already seen xn minus 1. So, obviously, W transpose xn means W0 xn, W1 xn minus 1, and there is summation, and that is equal to dn. So, you can alternatively write it like this. Now, you see one thing, if I take a vector, if I suppose take a vector here lying on this line, so between any 2 points, let it be W prime vector, that is W0 prime, W1 prime, and let it be W this. Okay. That is W prime is W0 prime, W1 prime, and W double prime means W0 double prime, W1 double prime. Okay. Then this vector will be what? It will be W double prime minus W prime. Okay. So, it will have coordinate, I mean this W. So, on this axis, this much will be W0 double prime minus W0 prime, and on this axis, if you draw a line, on this axis it will be W1 double prime minus W1 prime. All right, this is a vector. So, actually you can translate that vector and bring it here. as though this vector has been added to this point, this is another vector. If you have to do addition of the two vector, you pull it, bring it here, okay, and then you get this point. So, this vector lies on this plane, because I took 2 points on the plane, took the difference. This vector lies on the plane. Now, you see one thing, this point lies on the plane. So, W prime transpose x n, that is d n, again W double prime transpose this point x n, again d n. So, if I subtract, what I get is, subtract left hand side from left hand side, right hand side from right hand side, I get this W double prime minus W prime transpose. You can subtract first and then the transpose x n equal to 0, which means this vector, which is this vector, and x n, they are dot product. This is a vector, okay. You can call it a vector maybe u. So, this is my u, and u lies on this plane, okay. This vector lies on this plane. So, u transpose x n is 0. That means dot product between u and x n is 0. That means my x n will be at 90 degree to this plane, because then only they will be at 90 degree. So, this is my x n. All right, this is a property. Now, see one very interesting thing. I come back to the derivation of NLMS algorithm. First, at nth clock, you have a W n. Okay. So, this equation is W transpose x n is equal to d n, and this is my optimal point. This vector is W opt. So, the other equation, next equation for n plus 1th clock, that will be another straight line as you have seen, but it should still cut through this, go through this point, and this is my W transpose x n plus 1 as d n plus 1. Maybe it is not visible here, so let me erase this, let me write separately again. So, this equation is this is the situation. And what you just recall, what do you do? We project on this, we call this W n plus 1. Again project it on the next line. Corresponding vector we call W n plus 2 and so on and so forth. This is repetition of the old story. Now, suppose these two lines, this white and green, one for nth clock, another for n plus 1th clock, they are at 90 degree with each other, they are orthogonal to each other. Like I have got this straight line, which is W transpose x n is equal to d n. This is my optimal point. The other straight line is like this, W transpose x n plus 1 is equal to d n plus 1. Suppose this is the case, and here is your W n. Now, we have seen what is just this line only. Any vector here lying on this line, we have just seen previously, will be orthogonal to, that is at 90 degree with x n vector. So, x n vector This is the direction of xn vector. That is why W transpose xn. Okay. We have seen earlier, any vector on this line will be orthogonal to this. So, xn vector, fine. Now, let us follow the NLMS style. Okay, I project it here. So, this gives me W, this is my W n plus 1, this point. Next, I project this on this plane, but then since these two planes, these two lines and in a general set of hyperplanes are at 90 degrees each other, this is my perpendicular. So, I directly hit here, absolutely converging just in 2 steps. When does it happen? When the two planes are at 90 degree, or equivalently speaking, if it is x n for this plane, x n plus 1 vector will be in this direction or I mean 90 degrees each other. It could be on the opposite direction or this direction, does not matter, angles will be 90 degree with this, which means x n dot product x n plus 1, that will be 0 because they are at 90 degree, because this is 90 degree, I mean from the diagram only you can see. What does it mean? It means x transpose n x n plus 1 0. Okay. X transpose n means x n minus 1 when I have just 2 terms, and here that means x n into x n plus 1 plus, or maybe let me write this way, x n plus 1 into x n plus x n into x n minus 1, that is equal to 0. So, if I divide by 2, that is also 0. But what is this? I am multiplying 2 adjacent samples, n plus 1th, nth, n minus 1th, and then averaging. So, it is a rough estimate of correlation with a gap of 1. Now, I have just 2 elements. In general, I will have x transpose n x n plus 1 equal to 0 means it will be general, x n minus 1 dot x n minus capital N plus 1, and this one is and this is 0. Sorry, I am very sorry, I wrote wrongly. This n plus 1. So, n should be replaced by n plus 1. So, it is n plus 1, then n plus 1 minus 1. So, n dot n plus 1 minus n plus 1 like that. Now, if you multiply and this is equal to 0, if you multiply you will have more terms x n, that is x n plus 1 x n. Next is x n minus 1, and so on and so forth. Last is x n plus 1 minus n plus 1 and x n. So, n plus 1 minus n plus 1 means n minus capital N plus 2, and it is n minus capital N plus 1 equal to 0. Capital N number of terms, if you divide by 1 by n, right hand side still is 0, but it is a very good estimate of correlation with gap 1, n plus 1 n, n minus 1, n minus 1, n minus 2 like that. So, this is R x x 1. So, when R x x 1 is 0, in this case I am getting convergence very fast, just in 2 iterations and in the absence of noise, of course. Okay. I am just hitting the correct point. All right. Now, R x x 1 0 means, I mean, yes, this is a good example of white input. White input, you have R x x k equal to 0 for any non-zero k, k equal to plus minus 1, plus minus 2, dot 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 dot. So, Rx1 0, Rx2 0. Here I need only Rx1 to be 0 in this case. But you know, if there is any random process, we expect maximum correlation at the minimum gap. Their adjacent samples are highly correlated. If that is 0, further correlations at larger gaps will also be 0, close to 0, which means for white input, in the absence of noise, NLMS will converge very fast, just 2 iterations. But on the other hand, suppose they are not white, that is, this is not 0. Suppose this is not 0. Okay. So, not 0 means they are not at 90 degree. So, they will be like this, there will be an angle between them. So, I hit here, then hit here, then hit here like, and it will continue, it will take more and more iterations. Okay. I mean smaller the angle between the lines, and in the general case hyperplanes, I will have more and more iterations to converge. So, this is the problem of NLMS, its convergence it depends on the input autocorrelation. If the input is white or correlation between samples are less, it will converge faster, but if it is highly correlated, there is the angle between the lines is small, because if the angle between the lines is small means my x n is here and my x n plus 1 is here. They are no longer at 90 degree, they will have the same angle as the angle between these two lines. Okay. So, if the angle is less, x n plus 1, if you take the dot product, it will have larger value, it will not be 0, which means correlation will be high. So, if the correlation is high and not 0, that means angle between these two line perpendiculars, or that is x n and x 1 plus 1, or equivalently angle between the two lines, which is same as that. If you take this perpendicular and this angle between them and this, they are same. So, if the angle is less and less, that is they are highly correlated, the two lines also will be closer to each other and will take more and more iterations. So, for correlated input, as the correlation increases between the samples, we will take more and more iterations to converge. This is a problem of NLMS, and this is overcome, this is tackled in a further generalization, which is called affine projection algorithm, which is a more generalized version of NLMS APA. This we will consider in the next class. Thank you very much.